I have to make, exactly, I have to make up for that. The quiz was too easy.
No, thank you.
I can't be known as the easy teacher.
Yes, you
No, you can't be like, oh yeah, just take Jhevon's class, you get 100 just for showing up. No, that's not. So the next quiz is going to be like,
No, thank
it's
you.
going to be a nightmare.
No, thank you.
Okay, so I just realized something by looking at the syllabus, which I probably should have mentioned to my other classes. I guess I'll have to just email them. Test 1, I told you the date would be announced. So at this point I have a fair idea of when it's going to be. So I'm pretty sure that I would finish the material needed for test 1 by Friday. Which means
That means we have a 3 homeworks on Mondays.
which means we're done here on Monday. Which means we have
The coming Monday? But it's a Monday schedule.
When?
After President's Day?
Which day is a Monday?
No, it's not that one.
Which day is a Monday?
It's the 20th. This Tuesday, the 20th, and we have a Monday schedule.
Oh yeah, that's what we, so it's February 9th, which is a Friday. Or
4 is better.
I mean, I'd be okay with waiting till the following Tuesday, which is the Thursday.
Yeah.
Wait, that means we'd have a test and a quiz?
No.
I don't know, some teachers are weird like that.
No. So yeah, I'd be willing to do any one. You guys want to test on the Friday or the?
No, it's Tuesday.
Tuesday. No, Tuesday. I have a test on Friday already.
Yeah, I have a test on Friday as well.
3 exams I see.
Okay, so yeah, you guys are literally the first class of the day to hear about this, even though you're in my last class, or my last class here. So yeah, you guys actually, we're gonna give all the classes test on that day. Separate my calculator. So yeah, so test 1 will be on.
What's the format of your test?
Pretty much going to be 2 weeks from today, exactly. Let me actually make a note of that. I don't want to show up the 9th with a test. you guys are gonna just have to just do this. I'm like, I forgot. You're gonna be like, yeah, you guys have to do the test. Like, I wouldn't take the test back home and not give them out. I accidentally bring them on the 9th. You guys are taking them.
I really don't. I got her tired. Yeah, that's why we got Mr. Yeah, I didn't get that one.
Okay, so yeah, test 1, February 13th, lucky number. That's Tuesday.
Really long.
But I'll probably send an email reminder about that. Because I have to tell my other classes as well. Let's see, we're going to continue 1.3. 1.3 was talking about linear models.
Can you tell us a little bit about the format of the test before you start? Or is it on the syllabus?
Oh, I'll post a review for it.
Oh, okay.
And
That's fine.
when I post it, I'll email you guys. So
Okay.
the review will definitely be up at least a week before it's
Oh, thank you.
Because I just literally realized how close it was. While you guys were taking the quiz, I was like, oh, what? I think I'll be done by Friday. Okay, so linear models. Alright, so just want to remind you of something. How do you know when to use one? And in this class, there are going to be 2 main ways you'll know when you need to use a linear model. One is going to be you will specifically be told to do so. Right? So an example of that was that hot dog stand example that I did close to the beginning of class, where I specifically mentioned the number of hot dogs sold and the price had a linear relationship. So that would be using the phrases like linear relationship, would be actually in the problem, or something like proportionate or directly proportionate, which is less likely that I'll use that. Or phrases similar to that nature, right? So you'll be told something like, more than likely I'll give you this phrase. These two things have a linear relationship between them. You know that a straight line is what you're going to use to actually model that relationship. Okay? One reason for this is sometimes you have situations in which you're not sure what the best model is to use, and so math people will try to get away with being as simple as possible, believe it or not, and a linear relationship is one of the most simplest things. So if you ever have the suspicion that something might have a linear relationship, you might just try it, and you can actually measure your results with reality and see how well it fits. So sometimes you just throw it out there, it's a linear relationship, or I'll tell you, assume this is a linear relationship. And so you'll know you should be using a straight line to model that function. Another time when you actually won't be specifically told to use a linear relationship, but you should know to use a linear relationship, is if you're measuring a quantity that changes by a fixed absolute amount on a regular interval. Or at regular intervals. Right, the intervals can be measured in terms of time or distance or something else, but I can say after every hour it adds by this amount, after every mile it adds by this amount, or something like that. Right, so an example of this was in the car rental example that we did last time, where I said there was a flat fee to rent a car, but then you were charged $2 every additional mile, right? So that wasn't a case of a fixed absolute amount. Absolute means the magnitude is what's important, right? So it's actually the value $2 was repeatedly being added, and that value was fixed. There's some fixed absolute amount, right? And so something like that car rental example would be when you use a linear model, because you'd realize that thing where I said $2 every mile puts you in this situation. So those are the two situations in which you want to use a linear model. So that's kind of where we left off last time. Let's actually, now we're going to take some time. I'm just going to spit some things at you, and it's going to be probably boring because most of you know it already, but I need to make sure everyone's on the same page and these ideas are in the forefront. So a linear model basically means a straight line is the best function. So I'm going to remind you about straight lines, just some basic ideas. I'm not going to go as in-depth into this as I could, because I would expect most of you know about straight lines. Let's give me an equation of a straight line. General formula. The general formula.
X plus B.
Mx plus b. Okay? So this is a special form. It actually has a name. This is called the slope-intercept form for the equation of a line. In this form, your y is the dependent variable, your x is the independent variable, m and b are constants that have a certain meaning geometrically. M is the slope, and b is the y-intercept. So if you have a picture, you have a line that's doing like this, for example, where it crosses the y-axis, that is at the value b. That's called your y-intercept. Where you cross the x-axis, by the way, that is called your x-intercept. Right? That will be important for us later to know how to find x-intercepts. So that's the, for example, just a random example of a line. Okay? The slope, you can't really point to it on the picture because you develop it from the process. So let's actually talk about that. M is a measure of the steepness of the line. It can either be given, for example, going back to that car rental example, me telling you that it charges you $2 for every mile is me actually telling you the slope is $2, or the slope is 2. So it can be given, or someone can just say, this is the slope, use this for the slope. Or we can find it given 2 points. We need at least 2 points of reference here. We figure out a slope from 1 point. So given x1, y1, and x2, y2 are on a line, we have its slope is m equals, what's the formula?
Y2 minus y1 over x2.
Okay, everyone knows. Now, in general, it doesn't matter which point you choose to label x1, y1, and which point you choose to label x1, y2. Just make sure the orders match up, right? Vertically, the points should correspond. So the x value is right below corresponding y values. Okay? So that's called the slope formula given 2 points. It's basically the calculation that gives you the intuition of rise over run. Right? Tell me how fast, how high something is moving versus how long I've traveled to reach that height, and that kind of tells you how steep something is, right? If a rise is very high in a very short horizontal distance, it's very steep as opposed to otherwise. Okay? So you can be given, say, an x1 and a y1 and an x2 and a y2, and so the rise is this distance here. And that's just this length here, which is just this minus that. And the run would be here, which is just x2 minus x1, right minus that. So that we would have seen before, I believe. Just reminding you of how you can see these things on a graph. We can also find a line given 1 point and the slope. Let's say someone specifically gives us 1 point. Given m and a point x1, y1 on a line, its equation is y minus y1 equals m x minus x1. Another version of the equation of a line. Oftentimes, personally, I find it more easier to do with this one computationally, but it's really a matter of preference which one you use, y equals mx plus b or this one. So this is actually called the point slope form. So you have the slope-intercept form, y equals mx plus b, and you have the point slope form. So sometimes I won't actually care if you give me the form y equals mx plus b. You can literally just plug the numbers into this one and tell me that is the answer. That's why I think this is easier, because I'm not normally going to care about it, about what form, if I'm asked for the equation of a line. You might want to solve for y if your y is actually measuring something that you care about. Another thing you need to remember about a line is that the sign of the slope matters. Right? The behavior of your line depends a lot on the sign of your slope, whether it's positive or negative or zero. So for any straight line, there are really only 4 situations you can find yourself in. You can be in a situation where the line moves up as you go from left to right. You can move down as you go from left to right. You can stay steady as you move from left to right. Or it can literally go nowhere as you move from left to right. What's the sign of the slope in this scenario?
Positive.
Right, the slope is positive in this scenario. And when you know that a line has a positive slope, you can interpret that, as we said last class, in terms of increasing. A line with a positive slope is a line that's increasing. How you want to think of that as well is that it means the dependent variable is getting larger over time. So if you know that you're measuring the slope of a line, and you interpret your y value in some way, like your y value could be profits or cost or whatever, you can interpret from the slope whether your costs are rising or declining, right? And if the slope is positive, it means things are getting bigger, they're getting larger, they're increasing. This one here, the slope is negative, and that can be interpreted as decreasing. Meaning the quantity y is getting smaller, right? You can see that from the picture, but I also want you to be able to not even just have a picture, given certain information, you can already automatically interpret it as something getting smaller or decreasing. What's the slope in the case of a horizontal line? 0. Here m is equal to 0. So this means it's staying constant. Our independent variable is not moving, it's one constant value regardless of your independent variable. What's the slope for a vertical line?
Doesn't exist.
Right, it's undefined. Right? You have an infinite rise over 0 run. It's an undefined quantity. And basically that means that there's only one possible input, and then all possible outputs can happen for that one possible input. It's not even a function. Okay, so that wouldn't even apply to functions. So the slope has talks about certain behaviors of your line, and those behaviors can have interpretations based on what your quantities are representing. Or you can tell if something is getting bigger or something is getting smaller. Okay, so that's a very important notion. So I don't think that's anything you didn't know before, but I really want you to have these interpretations at the forefront of your mind. I can get rid of this, right?
Yeah.
Now, if you talk to any algebra student or any pre-calc student and you ask them about slope, they'll pretty much tell you exactly what I just told you. So, okay, when you hear the word slope, what do you think about? Oh, it's y2 minus y1 over x2 minus x1, or it's rise over run. It's how steep a line is. But as a calculus student, you want to have another interpretation for slope. Of slope. I'm going to illustrate how I want you to interpret this with an example, and it will be clear from the example how I want you to interpret slope. you're tracking an object and you're measuring its distance from a certain point. So the object is moving, there's a point you're watching. As soon as the object passes that point, you start your stopwatch, and you continuously measure the distance as it's moving over time. And you can actually plot this on a graph, where I put time on this axis. So this, just for definiteness, let's just say we're measuring that in hours. And let's say we're putting distance on this axis, and let's say we're measuring that in miles. So there's a point that you're keeping your eye on, you call that position 0, and so you start your stopwatch when its distance is 0 from the point and the time on your stopwatch is 0. But you're watching this object, and it moves in such a way that when you're measuring its distance, it ends up being a straight line when you're plotting all the points. And let's say after 2 hours, you measured its distance and you realize that its distance is 80. Question 1. What is the slope here? Yeah?
40 miles.
How did you get that?
I divided 80 miles, which is the rise.
Rise is 80. Run is 2. And that gives you 40. So the slope is 40. And question 2, or well, how do you interpret that 40? Is it just 40? 40 what? Miles per hour. The guy that's on the vertical axis is being measured in miles. So this 80 is not just a random 80, it's 80 miles is the interpretation you're putting on it. This 2 is not just a random 2, it's 2 hours is the interpretation I'm putting on it. Which means over here, you have miles per hour. Or this is just 40 miles per hour, mph. Right? So this would be 40 miles per hour. And how would you interpret that? What is that to you? If you had to describe that to someone, what would that measurement be? If you were to describe that measurement, miles per hour is a measure of what?
It's not velocity. It's not velocity. It's speed.
Technically it is velocity, but I'll take speed as the answer here because it's the same. Right? When your speed is positive, your velocity and your speed are the same. Okay. So it's speed. In other words, I can think of the slope of this straight line as a measurement of how fast y is changing with respect to x, which is a measure of speed. That's what speed is. The distance you're changing over the time. And so from now on, this is another interpretation I want you to put on the word slope. When you hear the word slope, of course you should be thinking y2 minus y1 over x2 minus x1. Or you should be thinking about it's the steepness of a line. But you should also be thinking of it from now on as a kind of speed. It's a kind of rate. It's kind of measuring how fast the dependent variable is changing with respect to the independent variable. When you think of slope, you can think of this as how fast y, or the dependent, this is general for a dependent variable, is changing with respect to x. So in the case of distance, I can, in this particular example, was measuring how distance is changing with respect to time. But we know what that measurement is. It's a speed. It's kind of telling you how fast something is going. The idea, though, here is if you want to get abstract, nothing was really special about how I labeled the axes, right? I didn't have to label it distance and time. right? I could have had that graph, and I could label it with something else. I could say, oh, it's the price over time. Or I could say it's label this profit and label this cost. Or label this number of items sold. Right? I can change the interpretation of these axes at any time I want. But at any given time, what that you can interpret that is, it's how fast this guy is changing on the vertical axis with regards to the number of items, right? Every time I sell one more item, how does that increase or decrease my profit? I can analyze it from that point. There's nothing special about the axis labels. So we can make this interpretation. More generally. So something you describe to it as someone who's never really taken calculus, the best word you could probably use is speed. Unless most people actually probably wouldn't even know velocity really, maybe. But at this point, in calculus, speed, you can think of slope as a rate of change, which is how fast something is changing. In particular, it's the rate of change of the dependent variable with respect to the independent variable. And from now on, that is another interpretation of slope in your consciousness. It's y2 minus y1 over x2 minus x1. It's the steepness of a line, but it's also a measure of rate of change. And I'll actually give you some other interpretation for slope as well. And note the sign still matters. Right? So if the slope is negative, you can think of slope as talking about a rate of change or how fast something is moving, but in particular if it's negative, it's how fast something is decreasing. You can also think of this if the slope is positive. It's a measure of how fast something is increasing. Super important interpretation for the slope of a line. It's a rate of change of a function, and it's a rate of change that can not only tell you how fast something is moving, it can tell you whether it's increasing or decreasing, whether something is getting bigger or something is getting smaller, and how fast it's doing this. And this is a super important interpretation of slope. It now should be at the forefront of your minds, because half of calculus is an answer to the so-called the rate problem, right? So you need to figure out how fast something is moving. Calculus is the answer to that. It's one of the things that calculus is about. It's really about two things, calculus. One of the things is an answer to the rate, how we can apply its answer to in various ways. And that's kind of it for 1.3. Yes, it's done. Or next time. So we're going to move on to 1.5 because we skipped 1.4. We're going to talk about exponential models. I mean, I already gave you two examples for these. The examples don't really change that much at this point. So about the definition. An exponential function is one of the form y equals a to the x. we'll assume our A is positive like this one. A is a constant. X is the independent variable. So for example, the function y equals 2 to the x is an exponential function. That's the name we'll give to it. Right, so you know about polynomials and radicals and all that stuff. I'm defining a new class of function, which a lot of you probably would have seen already, but I'm just reminding you. It's called an exponential function. Something like y equals 1/2 to the x, also an exponential function. Y equals pi to the x, also an exponential function. If I have y equals x squared, this is not an exponential function. Right? Don't just think just because something has a power, it's automatically an exponential function. An exponential function happens when the base is a constant and the power is a variable. If the base is a variable and the power is a constant, it's not exponential, it's something else. And in this case, it's a polynomial. So this is called an exponential function, anything that looks like that. Some important things to note. Exponential functions obey the laws of exponents. Right, so for example, I have one exponential function where the independent variable is described by y, and I multiply that by another guy where the independent variable is described by x and y respectively, then I can create a new exponential function that will be adding the two independent variables. Or I can take that guy and divide by that will be x to the a to the x minus y. Right? I know that a to the 0 at the point where the input is 0, because I'm not 0 as well, that will give us 1. Right, you know things like a to the minus x is actually 1 over a to the x. Or you can even describe it as 1 over a raised to the x, which is kind of what's going on here. You take a to the x over y. What is that? A to the x over y. Yeah?
A to the x minus y. Oh, wait.
No. Yeah?
Radical a to the x and outside of b plus 1.
Well, the y is on the thing right
Yeah.
here, right? So it's the y root of a to the x. Okay, etc. Right, so all your laws of exponents, they apply to these functions. It does not matter that the base is a constant, the power is a variable. When you multiply two things with the same base, you add the powers. All of that stuff is still true. And that will be very important when you're simplifying things and you need to solve equations and things of that sort. You should be aware that when dealing with exponential functions, the laws of exponents apply. So you can use them without fear. Other important things that you should recognize from exponential functions are their graphs. So you have y is equal to a to the x. A is greater than 0. In particular, a is not 1. If a is 1, it's just 1 to the x is just a horizontal line. It's not an exponential. But let's pretend it's positive, but it's not 1. In fact, if let's say a is greater than 1, in fact, the case where it's less than 1, we can deal with that. I'll show you how we can deal with that. But let's pretend a is greater than 1. What does the picture look like? Does anyone know? Exactly. It's like that. What does this cross?
The y-axis.
What? Yes, I know it crosses the y-axis. the point is at the point 1. Why? Because when you plug in x equals 0, this output is 1. Okay? It continually goes closer and closer to the x-axis here, but it never actually touches it. You say it's asymptotic to the x-axis. And another important thing you need to know about exponential functions is they also obey the laws of transformation. So for example, if I have y equals a to the minus x, that graph is just a reflection in the y-axis, right? And this would also cover the case where your a is less than 1, by the way. Because again, by that interpretation, this is just 1 over a to the x. So if my a is bigger than 1, this quantity will be less than 1. So that covers the cases where the number is less than 1. Right? But if you change the x to a negative x, it flips in the y-axis. Also, if you put a negative on the entire function, it flips in the x-axis. So if I do y equals minus a to the x, that's going to flip this guy into the x-axis. It's going to behave like that. And if you have y is equal to minus a to the minus x, that's going to take this guy and flip the x-axis, right? So transformations happen. You can shift it, you can add 1 to it to shift it up, right? You can subtract or add a value to the x to shift it horizontally. You can multiply it by a constant to stretch it. All that stuff will still work, right? But the basic graph is going to be this one. This is the one you're going to be manipulating in any given time. So it's important that you know this, but it's nice to have memorized all of these so you don't have to actually work it out when you're doing it. Knowing the graphs are going to be very important. Eventually we'll cover a topic called limits. And you can have a lot of situations when it comes to limits. You can do a lot of computations to be solving them, but a lot of the times knowing the picture in your head of the functions you're working with can, first of all, it can help you to not have to do computations at all, but it can also make computations easier. You kind of know what to look for, and your manipulations will change based on what the picture would look like. So it's very important to know the picture, and you'll see why it's important to know the picture later on, but it's very important that you know the picture. Okay, so at least that's the picture of an exponential. In calculus, there is one exponential function of particular importance. Does anyone happen to know what that is?
E to the x.
Hmm?
E to the x.
E to the x. Y equals e to the x. It even has a very conceited name. This function has the name, it's called the natural exponential. It's very natural for us to use this function. It's like, oh, you're working with exponentials? Naturally we'll use e to the x. In terms of calculus, it is the easiest exponential function to use. And a lot of the times when we are given other exponential functions, we want to be able to express them in terms of this exponential function. It's that important. Okay? It's e to the x. Now because, of course I say it's an exponential function, which tells you that e is actually a constant. E is a constant. Very important, right? E to the x and e are two very different kinds of functions. This is an exponential function, this is a constant, right? E is roughly 2.718281. It's an irrational number, right? So e represents a number. They use e to represent it because it's named after Euler, who was a mathematician back in the 1700s who managed to compute this number to like 20-something decimal places without the use of a calculator, without the use of supercomputers, which is pretty hard. So it's named after Euler, Swiss mathematician. Okay, so it's that number. E is, and at this point you probably won't understand what I'm talking about, but I'm going to kind of explain it here. But we will cover limits, which this symbol would start to make sense to you after a while. But you can actually express E as a limit, as that particular limit. And that's kind of where the number came from. So I don't really have any colored chalk, but let me sort of explain this expression. If you look at this guy, may or may not look familiar to you now, but I'll tell you where it's come from. This is the compound interest formula. This width. So you take the compound interest formula, set the time to 1 year, set the interest rate to 100%. N equals number of times compounded. Per year. So you're a greedy banker and you want to realize what's the most amount of money I can squeeze out of someone for a loan. So you say, you know what, I'm going to charge you 100% interest rate to borrow money from me for 1 year. And I will compound it, I'll hit you with that interest rate n times during the course of the year. Right? So there are many ways you can do this, right? You can do it, n could be equal to, for example, 1 time. So I hit you with interest at the end of the year. So that's becomes simple interest. Or 2 times a year, or 3 times a year, or 4 times a year, or 5 times a year. Or compounded daily like a credit card. So 365 is n. What if I said, you know what? Let's go crazy. I'm going to apply interest every second, every split second. The smallest amount of seconds you can imagine, I will apply interest more than that, more frequently. That's what this symbol represents, right? The number of times they're compounding is going off to infinity, going off without bound. It turns out that at the end of the year, the banker would not have made an infinite amount of money. He would only make 2.72 times what he originally invested in. So if you borrow $1 from me under this condition, at the end of the year, you will owe me $2.72. So it's a very strange number, and that's kind of where it came from. And it turns out that because it's this limit, it's very special. There are a lot of mathematical forms when they're working out formulas for stuff where this guy just pops up out of nowhere, and then it becomes very convenient to use it. So that's called the natural exponential function. We're going to talk a lot more about that. I'll give you a lot of rules that have to do with this function later. But for now, just know about its existence. And it's an exponential, so its graph looks like this because it's bigger than 1. Laws of exponents apply. Its picture is changed under transformations just as you would expect, etc., etc. It's just, it has a particular value that's very nice. And it shows up in a lot of contexts. And for calculus, it's the easiest exponential to do calculations with. That's why they call it the natural exponential. It's a very important number. So think of how important pi is to geometry. That's E with calculus, right? Pi shows up all over the place in geometry, right? E shows up all over the place in calculus. So, what else can I tell you? Now let's go to the title, Exponential Models. They're used all over the place, for one. In real life, you'll actually be more likely to apply an exponential model more than you're likely to apply a linear model, believe it or not. Applies all over the place. Let's say you're studying population dynamics. You're measuring populations. Could be people, could be a population of bacteria, population of rabbits, population of pigeons. An exponential function is going to show up somewhere in there. You could be measuring radiation. or fluid dynamics, right? So if you're measuring the radiation levels at Chernobyl, an exponential function is going to pop up somewhere. If you're measuring airflow through some tunnel, an exponential function more likely pop up. If you're measuring, there are a lot of engineering applications as well. Right? You want to model a piston motion in an engine, an exponential function is going to pop up. Right? Anything oscillating, a vibrating spring, an exponential function is going to pop up. They're very ubiquitous. So it happens in electricity. You're measuring forces moving in a circuit or resistance in a circuit. This guy is going to pop up. It's all over the place. Financial modeling. Right? This guy is going to pop up, right? The compound interest formula is an exponential function. We can think of it as that way because the power is the variable, right? So exponentials, they're all over the place. They're very ubiquitous. And in terms of calculus, if you want to apply calculus to something, the best exponential to use is the exponential e to the x. And you'll have plenty of spaces to use it. When to use? One, again, if you're told to do something. So just as how I might tell you, okay, these two quantities have a linear relationship, I can tell you these two quantities have an exponential relationship. Or this quantity grows exponentially, this quantity decreases exponentially. I can actually say that to you. But another way, if I don't say to you how you know you have to use an exponential function, if the quantity you're measuring changes by a fixed relative amount. By relative amount, I mean it changes by a percentage of the current amount, right? So you know you should use the equation of a line if you're changing by a fixed absolute value, right? If something is always increasing by $2, you should be using the equation of a line. But if something is increasing by a relative amount, if it's increasing by the percentage of the thing that's currently there, then you would use an exponential model, right? And that's a fixed model. So, for example, if you think about a population, right? You count literally the number of people, number of children that 10 people will have versus 100 people will have. It's not going to be measured linearly, right? Because you have to worry about these people have children, and then in the next generation, the children of the children will have children, right? The number of new people will grow more than a fixed amount over time, right? It will actually grow by a percentage amount of the current population. So any situation that has that kind of interpretation, you can use an exponential model. And we'll stop there. We're done with explanation. We're going to be going back to these when we learn about something new, but for now, that's the theory that we're trying to know about exponents.
We didn't finish 1.5.
Wait, we finished 3.5?
Yes, that's all I wanted to do.
No, but.
Wait, so is 1.3 and 1.5 due Friday?
Yes. 1.3 and 1.5 due on Friday, and